All metals, like this piece of aluminium, are crystalline, the essential features of a crystal being that its atoms are in regular patterns. This is not always apparent in an ordinary piece of metal, but if we etch it with an acid, regular pits are formed, and the light glinting on these pits shows the crystals. The regular pattern of atoms in a metal is generally one of close packing. This model, made of spheres, actually of table tennis balls, is a characteristic form. Small bubbles floating on a soap solution have very closely the same forces between them as the atoms in a metal. The surface tension draws the bubbles into contact, and the internal pressure sets a limit to their approach, as if small balloons were being pressed together. So we can make a model of a metal with these bubbles, which crystallizes itself. A tank is filled with soap solution. Air supplied by this aspirator is blown under constant pressure from this jet set just beneath the surface of the soap solution. The bubbles produced form a kind of crystalline raft, which is quite regular because the bubbles are so uniform in size. Here is a later stage in the formation of such a raft. The pattern has rows in 3 directions. It's just like the model made of spheres. When the raft of bubbles forms, it's generally in portions of pattern which are not parallel, or, as we should say, are distinct crystals. These meet at crystal boundaries. It can be seen in this raft that the rows are in different directions in neighboring crystals. This pattern of crystals in this larger raft is very similar to the pattern of crystals seen in an etched metal. A metal rod, deformed to a limited extent, springs back elastically to its original shape when released. The same is true of a raft of bubbles. Note this deformation at the places where bubbles are missing. If the rod is pushed too far, it gets a permanent deformation and does not come completely back. What happens on the atomic scale when this plastic deformation takes place? We believe that the bubble model supplies the answer. Dark lines are seen dashing about in certain directions along the close-packed rows. These are the dislocations which we are going to study in detail. By their movement, the general shape of the mass of bubbles alters, though its structure remains regular and crystalline. From the geometry of the deformation, it's clear that the sheets of atoms glide over each other, the closely packed planes slipping like a pack of cards. But all the atoms in a sheet do not jump from one position of packing to the next simultaneously, as they're doing here. A dislocation starts at one end and runs to the other like a ladder in a stocking. A dislocation can be thought of as a place where slip is terminated in mid-air. There's a row above which is not partnered by a row below. You've just seen the rows, and here is the corresponding arrangement of bubbles. The strain required to make a dislocation run across the crystal is far less than that which would be necessary if a whole row jumped at once. We must have some way of defining a dislocation quantitatively, and this is the purpose of the Berger's vector. We would draw a circuit which would close in a perfect crystal. If the circuit includes a vacant lattice site, it will still close exactly. If it includes a dislocation, it does not close. The residue is the Berger's vector. It's equal to an interatomic distance. However the circuit is drawn, the result is the same. The dislocation runs in a direction which relieves the strain. If the strain is reversed, it runs the other way. After it's passed, the crystal is perfect as before. Now that we've seen what a dislocation is, we can look again at the picture of dislocations moving in all directions as the crystal is deformed. It's still not certain how dislocations begin in a crystal. They may be left in the crystal as accidents of growth during rapid crystallization, as can be seen in the mass of bubbles which is building itself up here. They may also arise from groups of vacancies where atoms are missing. The line diagram shows how a pair of dislocations might be created in this way. Each parallelogram encloses an atom which is going to be taken away. The rows on either side of the missing atoms collapse together to make a pair of dislocations. The bubbles show the same thing happening. A few bubbles are burst with a hot wire, and two dislocations start from the holes so created. Dislocations are most likely to start where the stress is greatest, at cracks or notches, like this. Two or more Berger's vectors may be combined to give a resultant vector. This will be seen in the following series, where a circuit is run first round each dislocation separately and then around both. The combinations will now be shown taking place in the bubble model. You will see, first, two equal and opposite dislocations in the same row cancelling each other. There. Secondly, two in neighbouring rows combining but leaving a vacancy. Thirdly, dislocations leaving a complex of vacancies. Finally, you will see two dislocations whose resultant is not zero, approaching each other and turning into a third resultant dislocation which runs away in another direction. If a dislocation jumps from one row to another, it may remove a vacant site. The line diagram shows how this takes place. Now you will see it actually happening in the bubble model. Watch the vacancies in the bottom left-hand corner. Since the region around a dislocation is in a state of strain, there are forces between neighboring dislocations. First, we shall see two dislocations in relative positions of equilibrium. If one is displaced, it returns to position. Two similar dislocations on neighboring planes attract one another. These two refuse to part company. A number of similar dislocations attract in the same way and line up. An outsider cannot join the party if it's on the same plane as one in the row. But if we move it sideways onto another row by bursting a few bubbles, it joins up. Here's the whole row moving together and a latecomer hurrying to join their company. Two repelling dislocations are reluctant to pass. One drives the other before it. An impurity atom can be represented by a bubble of the wrong size. It interferes greatly with the movement of dislocations, and it's a center of trouble. A type of boundary may be anything between two extremes. If the angle of disorientation is small, it's like a row of dislocations. At larger angles, the nature of the boundary is more complex. With small angles, a plastic movement corresponds to an advance of the line of dislocations, as illustrated here. Here we see this movement in the bubble model. With larger angles, the sliding may take place along the disordered boundary. Here is the corresponding movement in the bubble model. Finally, the plastic movement is here taking place both by moving dislocations and by boundary sliding. All these processes we have seen play a part in restoring order to a much distorted raft. The distortions can be effected by stirring up the raft with glass rods. This corresponds to a violent deformation of the metal. The dislocations travel and combine so as to tidy up the areas of greatest strain and create a mass of nearly perfect crystals. These then adjust their boundaries so as to reduce their length as far as possible. The readjustment is at first very rapid, but it soon slows down, and in these shots it's much speeded up by the camera. The black spots which suddenly appear are due to bubbles bursting. Some small crystals disappear in this cleaning up process. Crystallization is impeded by impurity atoms. This small bubble, causing the local imperfection, was difficult to burst. The bubble model is far from being a complete representation of the metal structure. One serious disadvantage is its two-dimensional character, whereas a metal is, of course, three-dimensional. It is possible to make three-dimensional close-packed bubble masses. Each bubble lies between three others above and three below, as well as six around it, as these close-ups show. But the three-dimensional packing is hard to obtain except in a layer of a few sheets, and even if it were thicker, one could not see what happens inside. Another disadvantage is that one cannot set the bubbles in vibration and so simulate the agitation of heat motion. Nevertheless, the model suggests many ideas, and when we see the dislocations dashing about, we can form a mental picture of what is happening in the metal itself.